Welcome to the Computational Fabrication Seminar,
a web series showcasing new research, exciting ideas, and exchanging thoughts.
Our weekly 1-hour live sessions rotate through 3 different time zones and are jointly organized by IST Austria, University of Washington, and Singapore University of Technology and Design.
Each session starts with a motivational opening talk given by an expert from industry or a field related to computational fabrication, such as robotics, computer graphics, mechanical engineering, material science, HCI, applied math, design, or architecture.
The motivational talk is followed by a technical deep dive. We invite our audience to ask questions during the talks via YouTube comments and join us afterwards on Discord.
So good afternoon. My name is Michał Piłacz, and I will be the host for today. The theme of this week is architecture and programming languages and their use in computational design. And it's my great pleasure to introduce our motivational speaker for today, Karl Willis. Karl is a senior research manager at Autodesk Research, focused on data-driven design software and manufacturing. He holds a PhD in computational design from Cornell University and has presented his research internationally at conferences such as ACM SIGGRAPH, ACM UES Study, and ACM CHI. His work at Autodesk has won numerous awards, including Fast Company Innovation by Design Honoree and Core 77 Design Awards Research and Strategy Honoree. And today his talk will be about learning programs for fabricating the physical world. And the stage is yours, Karl.
Great, thanks. Okay, let's get started. So yeah, thanks for the intro. So today I'm going to talk about learning programs that we can use for fabricating physical objects in the world around us, and I'm going to try and set up a little bit of the motivation for some of the work we've been doing, and also like Kevin has been working on as well. So if you look around us, you can see that the parts and objects that surround us in the everyday life are actually really complex. If we sort of mentally break them into pieces and lay them out in front of us, we can see that they're made of hundreds or thousands of different pieces. And these are all sort of designed with an intention and a design intent attached to them, and come together to form functional objects. And of course, at Autodesk, we're very interested in making it easier for people to design these types of complex objects. And typically they're done using parametric CAD. And this is one of the dominant paradigms in how you design mechanical objects. And as you can see, each of these components are sort of designed and assembled to bring them together into a physical manufactured part. And so what this looks like is actually quite like a shape program or a CAD program, if you like, and that people, when they're designing these things, create dimensions and constraints and little rules that join together to form a type of a CAD program that can be used to compile this parametric CAD design into an actual 3D geometry. So what you're looking at here is setting up a 2D sketch and then revolving that, and where all of those parameters are defined by the user. So here you can see another example where the user is sort of changing a parameter here to increase the number of holes in this design, going from 3 to 8. And those changes, what's interesting about them is they flow downstream. So if you're creating documentation for manufacturing, if you want to send this out to be die cast, or if you're doing a simulation, all of those changes from the CAD program sort of flow on and enable manufacturing downstream. And so what really enables parametric CAD is the underlying 2D sketches. And you can set those up with very, very simple parameters or very complex ones. And in this example, the 2 parameters are hole size and width. And just by varying the numbers that you input into those parameters, you get very different results for the sketch. And of course, this sketch is then extruded and created into 3D and then manufactured. And this sort of setup really lends itself really well to certain types of parts, and especially like things like heat sinks, where they're very, very easy to sort of parameterize. And you can look at here, these are a bunch of different sort of catalog heat sinks that are out there, and these heat sinks are used to cool off and dissipate heat away from CPUs typically. And we can actually set that up in parametric CAD as a type of program, a template model, if you like, that has these different parameters attached, and it allows you to basically control and change the design dynamically. And what this looks like is you can create a template design and have a larger base or a smaller base, have shorter fins or taller fins, have fewer fins or more fins, and it enables you to really create a diverse number of designs. And this is a really powerful tool because at the end of the day, you often have these late baking changes, and you want to have a very flexible design that enables you to sort of make small changes and not have to redo a lot of work. But the challenge is really that parameterization of these models is actually quite hard, and setting them up to be quite flexible and robust to changes is not an easy task. And if we look at a couple of designs from out there in the from people out there in the wild, we can see that even just designing a simple table actually kind of is not as easy, and making it sort of flexible and robust is not as easy as it would sound. So if we wanted to, for example, make the legs shorter here, we can change one of these parameters, and here you can see that one leg has been made shorter, but the others are still long. So we have to sort of build into it the knowledge that all of the legs in a table are typically the same length, and that may seem kind of simple, but we have to sort of say that explicitly. We also can see that there's no sort of concept of symmetry. If we want to make the table longer, we can extend it on one side, but now, unless we tell the program to do it, it doesn't sort of extend it on the other side as well, because this user hasn't specified that. Or if we want to make the table shallower, here we run into the problem that the legs are not actually constrained to the side of the table. So when you make the tabletop shallower, all of a sudden the legs get detached, and you're no longer able to stand up and be a table anymore. If we look at another example, we see similar things happening, right? And again, one leg, if you're trying to make it longer, pops out, and this time it's popping out the top of the design. And you see this again and again, and it's a hard thing to actually kind of parameterize these things correctly. If we look at chairs as another example, we can see this happening again. And once you sort of begin to push and pull these dimensions too far out of the range that they've been designed for, you get some really odd things happening that are kind of not probably what the designer is intending. So I mean, that's kind of the problem as we see it. And we've been really interested in how we can apply learning-based approaches to generate shape programs. So combining the benefits of neural networks with program synthesis to be able to make these types of CAD programs. And we're really motivated by a couple of reasons. So one of them is that reverse engineering is a very, very common problem when you're designing these physical objects. And so often you might have a mesh and you want to actually have an editable CAD file, or you might have a scan of an actual physical design, and you might want to convert that into an editable CAD file to make a change and then basically create it again. And so that happens again and again. And even when you're transferring CAD files between software, oftentimes that whole parametric CAD history of how that design was created basically gets wiped away. Another reason is to be able to apply correct parameterizations, right? So we don't want to have a single parameter for don't want to have a parameter for every single one of these fins. We want to have one that applies to all of them. We also find that when you make these parametric designs, oftentimes the timeline gets really, really long, and all of the different steps you've made to create the design end up sort of creating these loops that may not be necessarily useful. And simplifying that design timeline makes it a lot easier to have these sort of dynamic designs that can be easily changed. So to tackle this problem, we've been working on and released a data set called the Autodesk Fusion 360 Gallery. And this combines around about just under 9,000 designs, and it releases not only the final geometry, but the actual sequence of modeling steps used to create them. So we provide a CAD program of sorts and individual geometries along the way to the final geometry. So this allows us, really for the first time to begin to learn not from, what was designed, but how it was designed along the way. And if we look at what we provide in each of the design files, it's a series of sketch and extrude operations that happen sequentially. And the sketches are 2D engineering sketches, and the extrude operations are how those sketches have been lifted into 3D. And when you sort of play back the sequence, it looks something like this, where each of those extrude operations, builds up a model, step by step over time. So these are some more examples, and you can see that they come from components of assemblies as well as from design files themselves. So they represent a pretty good cross section of the different types of things that people design using mechanical CAD tools. And sometimes they're complex. Oftentimes they're quite simple in terms of like washers or plates. And we're really hoping that we can use this data to try and learn how CAD files are constructed and learn how to create them. So this is the data set is essentially a series of sequential steps along with this CAD program, if you like. And you can check out the website here to take a closer look. And I'm going to hand off to Kevin now to talk about how he's in his work he's tackling some of these problems of reconstruction and reverse engineering of CAD models, and also dealing with how we might be able to create these parameterized sketches from using learning-based approaches. Okay, over to you, Kevin.
Oh, thank you very much for your inspiring talk. And I would like to remind the audience that they should post their questions into the YouTube live chat, and we will have a joint Q&A at the end of the session with both speakers. And today our deep dive speaker is Kevin Ellis, and Kevin works in program synthesis and artificial intelligence. He's a research scientist at Common Sense Machines and recently finished his PhD at MIT in cognitive science, co-advised by Josh Tannenbaum and Armando Solar-Lezama. Starting summer 2021, he's starting as an assistant professor at Cornell in the computer science department. And the stage is yours.
All right, thank you. Let me screen share. All right, so I'll be talking about work that I've done with my collaborators, and also some work that Karl has done, and it's going to be building on top of the kinds of problems that Karl laid out in his talk. So that's going to be about how to learn to use shaped languages for solving 3D reconstruction problems, and also how to extend those languages with parametric constructions for two-dimensional sketches. So that's going to be kind of the roadmap. We want to know how can we do reconstruction by program synthesis in a CAD-like language. And that's going to assume that we have the CAD language with all of its parametric routines or whatever. And then I'm going to switch gears and talk about how we can extend that language with new parametric routines that the system itself is going to learn. So starting with the first one, which is 3D reconstruction, I'll be talking about work that I did with Max Nye, Evan Poo, and Felix Sosa last year. And the kind of problem we considered was a very simple kind of 3D reconstruction where you see as input a three-dimensional voxel field, and then you want to infer a program in constructive solid geometry, a basic CAD language, which you can then use to reconstruct that object. So I'll illustrate the algorithm that we came up with for this simple CAD language, and then talk about some recent work on extending it to richer, more modern CAD representations. So the CAD language that we're considering is one where you're constructing a three-dimensional volume, and the language allows you to add and subtract volumes to make new volumes. And it also gives you a inventory of basic volumes. So these are parametric things like cuboids and spheres and cylinders. Even in this very simple language, though, the number of lines of code you could write, the effective branching factor of the search space over all programs is extremely high. In fact, it's over like 1 million lines of code. So if you imagine doing reconstruction when we're trying to find the program which best matches the specification, this is going to be a massive search space. So for example, imagine we had like the empty CAD program, and we were just saying like, okay, what could I write starting from this? Well, I could write a line which puts down maybe like one cuboid. There's a bunch of other cuboids I could put down. There's different cylinders I could put down. And there's like over 10 to the 6 different possibilities. For each of these choices, there's again over 1 million possibilities. And in general, we might have dozens of such lines of code to write, doing a total search space size, which is far larger than the number of atoms in the universe. So you might be thinking to yourself, well, maybe we could address this combinatorial search problem using deep learning. Particularly, could we train a neural net to just kind of tell us which branches to take in the search space? So could this learning approach save us? Well, actually, as I'm going to argue, the answer to that question is no, at least not on its own. And I'm going to explain why the most straightforward way of applying deep learning to this problem actually, I think, is does not scale. So imagine, for example, you took a voxel field and you wanted to pass it to a neural network, which acted as a kind of learned search policy, which was then going to output the lines of code in the program which would best reconstruct that input voxel field. So for example, maybe this neural network is like a language model, and it puts down like a cylinder command, then a cuboid command, then it unions those commands together, and so on. And imagine that our neural network is really good. And in particular, imagine that it's like 90% accurate. So for each of these lines of code, we have a 90% probability of getting it right. So that sounds quite good, except that as the number of lines of code becomes very large, as it becomes more like 20 or 30 lines of code, the probability of success decays exponentially. It goes down like 0.9 to the power of the number of lines of code. And that means that this is just not going to scale to long, complicated graphics programs. So there are some works which take an approach very much like this. And I've cited 2 of them here, but they tend to limit themselves to spaces of programs where the programs are fairly short, and they often kind of restrict the different lines of code you could write, which give the branching factor to be much lower. So if this doesn't work, then we should ask ourselves, why isn't it working? And in particular, why are human beings able to write long, complicated CAD programs? Well, one basic observation is that this approach is trying to write out the entire program all at once from scratch. So it just looks at the target image or voxels or whatever, and then spits out the whole program. In contrast, that's not how humans write code. Software engineers don't write out a big function and then expect it to just kind of work on the first try. Instead, they kind of interactively run and test their code inside of debuggers or interpreters or tools like that. And analogously, 3D designers build complicated 3D models by interacting with a piece of software like Blender or Maya or Fusion, and they're really rendering it at intermediate stages of construction, the timeline that Karl was referring to earlier. So you can think of these kind of interactive development environments as being a read, eval, print loop, or a REPL. So it's like what you get when you just run the Python interpreter and start punching in lines of code. And analogously, in something like Blender, you get to see the shape at every stage of construction, and you get to interact with all of the intermediate aspects of that stage of construction, like the vertices and faces and things like that. So it's not doing it all in one shot, it's doing it kind of incrementally. So this suggests that we should use learning, but couple it to something that's kind of like a read, eval, print loop, or a REPL. So we have an algorithm which does program synthesis, and we designed it specifically with 3D reconstruction in mind, and it tries to address this combinatorial search challenge by executing programs inside of a REPL, which for graphics or for shape programs means that the programs are being rendered at every intermediate stage of construction, and the learned model can look at that rendering. So concretely, our approach alternates between writing a new line of code, executing that code in the REPL, so rendering it to see what it looks like, and then assessing using another learned model to see whether that rendering looks like it's kind of making progress toward the goal. And then we wrap all of this up in a symbolic tree search over that large combinatorial search space. So this approach does use learning in some places, so in particular for writing and assessing code. But when you're executing code or when you're doing the tree search, there you're using ideas from programming languages, namely the REPL, or ideas from symbolic AI, namely tree search. So it's kind of a combination of learning and ideas from programming languages and AI. So here's how writing code works and how executing it works and how they interact. So you can think of code as being written by a neural network called a policy, which I'm going to notate as pi. And pi you can think of as a function, a neural network, which takes as input a spec, so like a voxel field or an image. And it also takes as input the current state of the REPL. So that's going to be a set of renderings, so the set of different volumes that have been constructed. And it's going to output a distribution over new lines of code. So just to make this concrete and visualize what's going on, imagine that we wanted to write a program which built this 2D image of a wrench. So this is our specification or our spec. And initially, our program is empty, which I'm notating with the empty set. So if we pass the empty set to the REPL, it just says, okay, the program is empty. So we get a kind of empty state. And then we pass this empty state and this goal image, the specification, to the policy, the neural network pi. The policy outputs a new line of code, which here says, like, draw a circle at some position with some radius. And that gets added to our current set of program expressions that we built up. So this thing here is kind of like the timeline. If you pass that through the REPL, though, it gets rendered into the circle. And the policy only looks at the rendering of the current state. It doesn't look at the syntax of the timeline. And you just sort of repeat this process over and over again. So the next REPL state, the policy has produced this rectangle, which gets subtracted to give you the head of the wrench, and so on. And eventually what you end up with is a reconstruction of the wrench, but also in the timeline down here, you get the syntax tree of the program. So if you look at this diagram showing the interaction between the REPL and the policy, one key thing is that the policy only doesn't ever look at code. It only ever looks at renderings of code. So there's kind of a conceptual separation here between syntax and semantics. There's the syntactic space of program expression trees. These are syntax trees. And then there's the semantic space of images, or in 3D volumes. And the REPL is only looking at images or volumes. And this means that it's kind of, you can think of this as intuitively semantics screens off syntax. Like, conditioned on semantics, you should be independent of syntax. And this kind of conditional independence assumption allows the policy to generalize better because it is no longer sensitive by construction to any details of the syntax of the program that it's building. So in addition to the policy which writes code, we also train a neural network which assesses whether code that's being written is on the right track. So we're going to call this neural network a value function. And just like the policy takes as input renderings of the current state, as well as specification, the value function is going to do the exact same thing, but it's going to instead output the probability of the long-term success of the policy in successfully reconstructing the input specification. And then we're going to use the policy and the value function together to do a kind of symbolic tree search over the search space. So the way that that interaction works between the policy, value, and tree search is as follows. Imagine that we had some input voxel field, like this simple model of a chair, and we started with just the empty program, here written as the empty set. So the policy would initially propose a few different shape drawing commands. Here are a few different proposals from the policy. And then what the value function does is it steps in and it downweights proposals from the policy, which it thinks are less promising, and it upweights proposals which it thinks are more promising. And more of the search budget ends up being allocated to branches of the search space that the value function thinks are more promising. So here, as you see, the top proposal from the policy is this cylinder, and it's kind of tilted wrong, which doesn't match up with how the chair should be, so the value function downweights it. Whereas when the policy proposes something that looks like the base of the chair, it upweights that branch of the search tree and spends more time exploring that region of the space. And then we repeatedly interleave the policy and value function and eventually converge on the final reconstruction. So as you can see right here, for example, the value function steps in and just discards this branch of the search tree because it knows right away that this is not on track toward correctly reconstructing the chair. So this is how we use the policy and value function. I'm going to describe how we train them. So one way of training the policy would be through imitation learning. So that means sampling action traces from randomly generated programs and then just supervising on those action traces. So imagine you have like a data set D of actions and specifications and also the partial program, so the REPL state. Then here our actions would be lines of code, our specification would be pixels or voxels, and our partial program would be the timeline so far, or the set of syntax trees that we've built up. So doing maximum likelihood estimation of the policy parameters would mean just maximizing this using gradient descent. And remember that the policy doesn't really depend on the syntax of the partial programs. It only depends on its semantics. There's a separation between syntax and semantics. And you can write that here by using these denotation brackets, which mean to take a program and then execute it to get its outputs. So that corresponds to the REPL. So imitation learning is nice because you can kind of bootstrap it from a very poor policy, but once you have a policy, you can then fine tune with reinforcement learning. So if we have some reward function that measures the degree of alignment between the geometry that we want and the geometry that we actually got, then we can slip that reward function into our training objective as follows to get like a reinforce objective function. So the only change here is you just compute the expectation over samples from the policy instead of samples from D, from the random data. And you just scale these likelihoods by the return that you get or the reward that you get. So this is a fairly standard setup for training neural program synthesizers. Like you pre-train with imitation and then you fine tune with reinforce. For the value function though, this is something a little bit different that we're doing here. So remember that the value function takes as input the specification and a partial program, and its job is to output the expected long-term reward of continuing to do a policy rollout along that part of the search space. So imagine that our reward is just 0 and 1. Like either we didn't match the spec, so we get a reward of 0, or we match it and we get a reward of 1. So in that case, the expected reward is actually the probability of getting a reward. So the expected reward is probability that reward is equal to 1, meaning that we're trying to just estimate for a given state, like, are we going to eventually get any reward at all? So that means that our value function is actually doing something fairly simple, which is just binary classification. It's really just saying, will this state eventually give me a reward? So we can train it with just cross entropy on rollouts. So there's a number of ways that you could use the policy and value to do tree search. But basically, you can use pretty much any off-the-shelf algorithm which has both a way of measuring cost so far as well as cost to go. So for example, in beam search, we could do like a beam search over the search space by measuring cost so far under the policy, and then measuring the cost to go as a kind of heuristic function in the A-star sense of a heuristic by taking the negative log probability under the value function. So if you look at this equation, the units for each of these expressions are actually the same. The units here are both bits of description length, and the cost so far is how many bits of description length you've used in writing the code that you've written to this point in time. And the heuristic cost to go is a learned estimate of how many bits of code or how many bits of entropy will need to be consumed in order to write a correct program, which is a suffix of the program so far. So it has this nice interpretation in terms of bits of information. Another approach that you can use in addition to like beam search is sequential Monte Carlo. So you can think of this as like a particle filter where your hidden states are transitioning under the policy. So your hidden state is a program, and the policy is changing that hidden state over time. And your observation model is given by the value function. So the value function is going to be reweighting and resampling particles or program states, which it thinks are on the according to whether it thinks that they're on the right track. So here's an example of these different choices on some 2D and 3D data. So on the right, you can see some randomly generated 3D volumes. And on the top is the target geometry. And then immediately underneath it is the full model with a sequential Monte Carlo sampler. Underneath that is just policy rollouts. So if you were to get rid of the value function. And then underneath that are two different kinds of beam search, either with or without the value function. And then on the very bottom is the reconstruction that you get if you don't have this REPL. So what you can see is that this REPL really does help. Like you need to be able to look at the thing that you're trying to build as you're building it. And also that a value function helps. So not just learning to look at the intermediate states, but also learning which intermediate states appear to be more promising. And empirically, the sequential Monte Carlo sampling scheme outperforms the beam search search algorithm. One of the reasons for that is because sequential Monte Carlo can kind of dynamically allocate its particles to be more densely packed in regions of the search space that look more promising. So I think this is like a particle filter, you're gonna have more particles that are densely in some region of the search space, whereas a beam always has the same number of particles and it doesn't densely pack them as efficiently. What we also found is that you really need these search algorithms in order to get some kind of out-of-sample generalization. So the kind of out-of-sample generalization we're looking at is generalizing to a larger number of lines of code at test than we're seeing at train. So for example, if we train on things with under 25 lines of code and then test with things with 40 or 60 lines of code, you find that you really do need explicit symbolic tree search combined with learning in order to get the kind of generalization. So here for each of these search algorithms, we're plotting the reward that we get as a function of how long we spend searching. So here I'm saying that tree search really matters and that learning is also important. But if you look at the and also if you compare like the kind of handcrafted test examples that we made, so these kind of quasi real objects, like these look very different from the like randomly constructed objects. But when you have both learning and search, you can generalize to these things that look less random than at train time. So you do need, I think, learning and search, but here the learning was fairly simple because the CAD language was fairly simple. The neural network is mostly just a bunch of CNNs, convolutional networks, which take as input images of the spec as well as the canvases built so far, and then they just pass that to a recurrent neural network, which spits out the next line of code. But if you had a more sophisticated neural net, then you could address more rich and more realistic CAD languages, like what Karl was showing earlier. Here's an example of a sketching and extruding like CAD language. In this Fusion 360 gallery work that Karl and Evan and other collaborators did, they showed that if you can build a kind of REPL which operates over the internal data structure of the CAD environment for this CAD language. So the internal representation here is a boundary representation. So it's something which knows about the faces and vertices and edges of both the target geometry and also of the geometry that we built so far. And the neural network is actually a graph neural network which passes messages over this graph data structure. And when you do that, what you can do is you can get a policy whose rollouts for 3D reconstruction can look quite close to actually the ground truth rollouts, or sorry, the ground truth timelines, which are used to build these kinds of shapes. So there's a few things to take from this. One is that if you have a REPL, then program synthesis can be made more tractable using a combination of search and learning. But in order to do that, you need to be able to actually execute all the intermediate programs you're building, but that's mostly true for shape programming languages. This work assumes that you already have a shape programming language, but it's possible to slightly relax that requirement, as I'll be talking about briefly next. So now I'll be talking about extending shape programming languages, where we're going to try and learn parametric modeling operations, which are going to be added to the language over time. So this is work that I did with a number of collaborators, mainly Kathy, Max, Matthias, and Lucas, and others. And the way I want to frame this work is that we're really trying to learn two things. One is we're trying to learn the domain-specific language, and we're also going to try and learn the search strategy. So we're going to try and learn the thing that we were learning with REPL, but we're also, on top of that, going to try and learn something about the domain-specific language, which is going to include here two-dimensional drawing routines. So for example, imagine that you wanted to learn a program which fit the points on this polynomial curve. So in order to do that, you would need to have concepts or things in your domain-specific language, like cubic functions and linear functions. And you also need to be able to look at this picture and say, oh, those are like the right concepts to use in order to solve this problem. So we have an algorithm which does that, and I'm going to illustrate it not in a graphic setting, but in a kind of classic program synthesis setting, and then show how it also applies to 2D sketches. So imagine that you wanted to solve a classic synthesis problem like learning to sort a list of numbers. So you want to maybe write a program which satisfies inputs and outputs that you see on the right, and you have a programming language which initially has programming routines like those shown on the left, so things like map and fold. So somehow we need to bridge the gap between the primitives on the left and the problem on the right. So the algorithm which we have for solving this problem doesn't just look at one synthesis task in isolation. It looks at a broad spectrum of tasks and tries to solve them, and incrementally adds new parametric routines or new subroutines to its collection of primitives. So when you run this algorithm on a corpus of programming problems, one of the first functions that it decides to add to its set of primitives is this routine here, which is called filter, and it takes a predicate and a list and filters out or removes all the elements which do not satisfy that predicate. And this is useful for sorting, but it's not quite there. And if you look sort of deeper into the set of functions that it's learning, it later builds on top of filter to write a routine which calculates the maximum element of a list, which looks even closer to sorting, and eventually defines a procedure which gets the nth largest element of a list, which is very close to sorting. And once you have this function here, it's really easy to write something which sorts a list of numbers. Now, in principle, you didn't need this learned library of parametric routines in order to sort a list of numbers. You could have just expressed it in terms of map and fold. And that's what I'm showing here. But this program is so long that it would take far longer than the age of the universe in order to find it using any kind of brute force search algorithm. Whereas once you have this learned library of parametric routines, it's much easier to solve the combinatorial search problem of getting to this sorting algorithm. So now I'm going to describe the algorithm which built up this library and solved this sorting problem. And this algorithm is called Dreamcoder, and the reason why it has that name is because it's a kind of wake-sleep algorithm, sort of like the Helmholtz machine. Like other wake-sleep algorithms, it has a wake phase, which here corresponds to solving problems or synthesis tasks by writing programs, as well as a pair of interleaved sleep phases. So in what I'm calling abstraction sleep, it's going to add new parametric routines to its library of primitives. And during what I'm going to call dream sleep, it trains a neural network, which is going to act as a search policy for program synthesis. So you can think of it as a hierarchical Bayesian model where there's some library of parametric routines from which we're going to write programs, and each of those programs is going to solve some synthesis tasks. And our job is both to infer the programs and also to infer the parametric routines. We're also, though, going to train a neural network, a kind of search policy, like in the REPL, which is going to look at a particular synthesis task and infer a distribution over programs that are likely to solve it. So now, if you look at this model here, there's really three things we don't know. We don't know the programs, we don't know the library, and we don't know the neural network weights. So that motivates a three-step iterative inference procedure where you hold each of those things fixed and then solve for one of the remaining ones. So those correspond to the wake, abstraction, and dreaming phases of this algorithm. So during the wake phase, we're going to hold the library fixed and solve for programs that solve each of the tasks. So we take a task, pass it to a neural network called the recognition, which we're calling the recognition model, which is going to guide a search over the space of programs. And we're going to search until we either solve the task, finding a program, or until we reach a timeout. During the dreaming phase of sleep, we're going to train the neural network to look at a program and predict, or sorry, look at a task and predict what kind of program would solve it. So it's going to be trained on pairs of programs and tasks, and we can get those from two sources of data. One is we could just replay programs that we found during waking and say that when you see the task of that program solved, predict that program. So that's a very simple kind of data generation or self-supervision. Another kind of self-supervision, though, is to take the library of parametric routines and just build random programs and run them to see what they do. And the advantage of this is that you can build as many random programs as you want. But the disadvantage is that if the parametric routines don't look very much like the kinds of programs that you actually need to synthesize, then these random programs are going to be very messy and noisy, and they're not going to look like real data. So we have these two data sources, these two kinds of self-supervision, one which just replays programs that we found during waking, and the other one which assembles random programs, and which we're calling here fantasies in reference to the Helmholtz machine. So during the abstraction phase of sleep, we're going to hold the programs fixed, and we're going to update our library of parametric routines. So the way that that works is we take programs that we found during waking, and we replay them, and we look at their syntax trees, and we try to find common subtrees or fragments of subtrees which we can identify. And when we find these matching subtrees, we can then pull out those expressions and add them to the library. And I'll be illustrating this refactoring for a 2D sketch language. So the kind of technical machinery which goes into this uses some data structures from the programming languages community, like version spaces and equivalence graphs, that have been kind of popular in optimizing compilers and in program synthesis. You should check out our paper if you want to learn more about how the refactoring algorithm works in detail. So I want to illustrate how this algorithm operates in a 2D graphics language. So here what we did is we took these 2D visual designs, which were originally generated in a logo turtle graphics language, so a language where the system controls a pen, which it can move across a canvas. And its job is to look at each of these images and then synthesize a program in this language which would reconstruct that two-dimensional pattern. So this is really inspired, or partially inspired by engineering sketches. So if you want to make a 3D object like this, you often have these like two-dimensional sketches that you lay out, and each of these has like parameters. So you can think of the problem of inferring a particular logographics problem as being like a much simpler version of inferring a particular engineering sketch program. And you can think of this refactoring that's coming up with new parametric drawing routines as being like coming up with parametric versions of these sketches. So each of these parameters, for example, would change different dimensions of the sketch. So we're really trying to do the synthesis at two levels, both of individual sketches, but also of the parametric routines, which are useful for modeling the ways that lots of different sketches could be related or varied. So again, these are the tasks, the sketching tasks that we're running it on. We have a total of 160 of these drawings. And when you run the algorithm on these drawings, here's what comes out of it. So this is an action-packed figure, so I'll kind of break it down in pieces. On the left are initial primitives that are given to the system, so things like loops and angles and arithmetic and pen movements. On the right are some different two-dimensional sketches that it has to draw, and beneath each of these sketches, the program that it wrote in order to draw them. In the middle, you can see each of the different parametric drawing routines that it added to its library in order to reconstruct each of these sketches. So for example, for this swirly beach ball sketch, it solved it by calling out to its learned parametric routine function 8 and its learned parametric routine function 4. If you look at function 4, it's a parametric routine for drawing spirals. And if you look at function 8, it takes another parametric routine and then spins it around in a circle. So that makes a lot of sense, because if you look at this swirly beach ball, it kind of looks like a spiral that's been like spun around in a circle. So function 8, I think, is fairly interesting because it's really a higher order function. It takes as input another drawing routine and a natural number, and then computes a radially symmetric version of that original drawing routine. And if you look at this learn library, you see other kinds of parametric drawing routines for things like circles or arcs. Now, this learn library is kind of like the system's declarative knowledge of what programs tend to look like. But at the same time, it's also learning a search policy, which you can think of as like procedural knowledge. So it's a neural network that helps it like search for solutions to problems. That neural network is trained on randomly generated programs, those fantasies I was referring to earlier. And it's useful to look at the evolution of those fantasies over the system's learning trajectory. So early on in training, randomly generated programs should be fairly simple and random looking. So here are some randomly generated programs at the initial state of learning, and I'm color coding them to show how the system drew each of these pictures. So it started drawing them in light pink and ended drawing them in dark purple. Actually, these are kind of the most interesting examples from 150 draws, because almost all the random samples are just either blank canvases or single line segments. So now we should look at what these random fantasies look like at the end state of learning. So at the end state of learning, what you see is a kind of recombination of all of the parametric drawing routines that the system learned in the process of solving each of these drawing problems. So it's kind of like recombining all of its learned abstractions, and this gives a infinite source of highly varied training data. So, if you want to train a neural network to help search for programs, it's much better to train on data that looks like this than to train on data that looks like this. And for fair comparison, these are also the most interesting draws from 150 samples. So that's why these tend to look more complicated than the training data. But in general, I think that the qualitative difference between these samples and these samples is very clear. So there's a few open directions that I wanted to put out here. One is that the work that I've discussed here is still very preliminary and clearly does not rise to meet the modeling challenges that Karl pointed to in his motivational talk. And so I think it's a really open question for how we scale these kinds of techniques to real world modeling programs. This REPL idea, although I think it's very scalable, also inherits a lot of limitations from the fact that it relies upon having to render or execute every single intermediate program. So in particular, if you have a program with symmetries, like geometric symmetries in a shape program, or control flow, if you have things like loops, then suddenly this REPL kind of breaks down. I think that there's ways of addressing this by using other ideas from the programming languages community, but it's really like an open problem. And last, how else can we learn reusable parametric modeling routines which are useful for human designers and engineers? Right now, the system tries to find the modeling routines or the reused abstractions which best compress the data, but that might not be the kinds of abstractions which are most useful for human designers and engineers. So there's an interesting question here about inductive bias. So that's it. And thank you to the organizers.
And thank you very much for this inspiring and awesome talk. So we will now start the joint Q&A session. And I do have a first question for Karl. So when learning designs from data, is the resulting design space mainly an interpolation of what people generally design, or is there some hope for extrapolation or discovering truly new designs?
That's a very good question. Yes, I think for the problem we've tackled, we've mainly been looking at the sort of reconstruction problem, and so we haven't done any work to date that looks at sort of generating novel designs, but I think that's something that we're hoping to do, yeah, in the future. So I mean, maybe watch the space, I think, is the answer.
Thank you very much. So now a couple of questions for Kevin. There can be many different CAD programs that you can generate that also create the same looking shape. So are you somehow dealing with this ambiguity? Are you evaluating sort of which programs look more natural? And along with this question, also a similar one, how do the programs that are generated actually look like? Do they look like something that a person would write, or do they look compressed and robotic-like?
Yeah. So the main inductive bias that's being used here is for compression. So it's trying to find the shortest program. But in Dreamcoder, we're trying to find not the shortest program for any one problem, but we're trying to find the shortest programs for all the problems, where if you reuse something in your library, so if you repeatedly reuse some parametric modeling routine, then you only sort of pay for it once when it's defined in the library. So it's like compression, but with a bias toward reuse of repeated abstractions. So sometimes this does give things that look kind of unnatural. And I think that's partly because the right inductive bias for humans is it's sort of compression. Like we sort of want to come up with libraries that reuse pieces across lots of problems, but there's also other kinds of biases that we bring to the table. Like we often want to have library routines which map onto the kinds of concepts that are in language or are part of our common sense. So there's kind of like a bias toward compression, but also like a bias toward familiarity. So for example, in like the NumPy library, one thing that's very different between NumPy and like the libraries that Dreamcoder makes is that NumPy has a lot of redundancy. Like if you want to take the transpose of a matrix, you can say dot capital T, or you can say dot transpose 0, 1. And Dreamcoder would never want that kind of redundancy because it's not very compressive. So what you end up seeing is this kind of mixing and matching of very natural human-like concepts. So things like circles and spirals, but then also defining other kind of stranger concepts like that parametric arc concept that I showed earlier. So for example, I expected it to discover like that circles were a useful concept. I did not expect for it to discover that this parametric arc thing was a useful concept. So you sort of see both. And I think that, that last open direction that I pointed toward about coming up with good inductive biases, which go beyond compression, is something that we should work on, and which would hopefully address this problem and make the programs that are synthesized be more useful for human engineers and designers.
Okay, thank you very much. So a question along these lines, since there is already some biases inside, do you have some sort of encouragement for the network to diversify the proposals of the policy that it has? Or can it happen that many similar branches are explored because they have very similar high value?
There is no reward for having a diverse covering of the search space. Whenever there's uncertainty in the posterior of a program, so when there's multiple programs which could work well for solving a problem, then the kinds of probability distributions that it's learning will naturally try to cover that uncertainty, but it's not baked in as a part of the search algorithm. So
a question for Karl. To switch gears from parametric designs, do you have any thoughts on making the explorative process a bit easier?
Explorative process. Yeah, that's a good $1 million question right there. Yeah, so I think like we can think of a lot of the sort of efficiencies we can get from sort of using some of these learning-based approaches as types of automation. And I think like there's just so much sort of non-human, like humans don't add a lot of value to a lot of the things, the operations they do today when they're designing things. And if you take the example of the snowblower, right? Like, somebody actually has to sort of go in there and position all of those individual screws and washers all together to make that large assembly. So I kind of imagine how much sort of work could potentially be done by some smarter algorithm. And I think most of the work we've been focusing on now is like, how do we sort of get rid of a lot of that kind of redundant work and try and free up some space for folks to kind of work on the parts that are really important to them. I think it's an entirely different question about how we can enable people to make better designs just in general. I think one approach to that though is being explored with generative design, and we sort of talk about like topology optimization for that, where you can at a high level, if you can sort of use simulation to basically either not only just for validation of an existing design, but perhaps to sort of show you a way that some other orthogonal design may help to solve a similar type of problem. I think that's one avenue, because then you're really sort of trying to put that design or an idea for a design into an environment, sort of see how it might perform and then be able to sort of choose between, different variants of that design, because I think that's sort of where you get the fanning out of different options in a design. So I mean, that's an exciting area, but yeah, I think there's a whole wide open space of how we can improve exploration design tools.
Thank you very much. And we have time for one last question for Kevin. In real CAD programs, there are often cases where designers use construction operations that are not really useful to get to the final design now. They are not improving at the moment, but they're improving sort of in the future by making certain lines and drawings easier. So can the proposed approach handle such cases, or would it be possible to extend it to also such construction lines?
Yeah. First, the CAD experiments that we did don't really test the model's ability to have that kind of foresight. But in principle, the policy and value function should be able to cooperate in a way which should automatically learn to do that. So in analogy to like AlphaGo, AlphaGo could definitely learn to make moves which in the short term don't look that great, but in the long term pay off, because it can learn an intuition in the policy about what moves are good in the long run, and also an intuition about what states are good in the value function in the long run. So the value function can learn to increase its estimates for things that look like they have good long-term prospects. And then the tree search can home in on the parts of the source space which the policy and value networks are pushing it toward. So in principle, these learning-based approaches should actually be very good at those kinds of things. But that's all modular disclaimer that I haven't done the experiment to actually show that that's the case. But in principle, that it should do that.
Yes. Thank you very much for the answer. And thank you very much for giving these two great talks at our seminar. And I would like to remind the audience that our speakers will be available for further questions at the Discord chat after this session. And with that, I would like to say goodbye and see you next week on our second talk. So bye-bye.